In our previous video, we have studied indirect method for testing of DC machines, that is Swinburne's test. In Swinburne's test, we operate the motor at no load and therefore we cannot check the actual operating conditions like temperature rise, commutation, etc. when the machine is loaded up to full load. We can overcome this drawback if the machine is tested with the help of regenerative method, that is by using Hopkinson's test. In this video, we will study the procedure of testing the machine using Hopkinson's test. Hopkinson's test, it is a regenerative type test. Means here we use two machines. Output of second machine is fed back to the first machine. That's why it is called as regenerative type test. And the method is also called as back to back test. The advantage of Hopkinson's test is we can load the machine up to full load without wasting their outputs. So we have studied in our previous video testing of machine by direct loading. So in that test we can load the machine up to full load, but the entire output power must be wasted. Here the advantage is without wasting their outputs we can load the two machines up to full load. But the limitation of Hopkinson's test is we need two identical machines. So here we have to use two machines, machine 1 and machine 2, which must be identical to each other, and the two machines must be mechanically coupled with each other. So here these two machines, that is machine 2 and machine 1, these are mechanically coupled. So this symbol, it shows mechanical coupling between machine 1 and machine 2. Means shafts of these two machines are mechanically coupled with each other. Now here we can adjust the field current of machine 1 and machine 2. So with the help of field rheostat R1, we can adjust the field current of machine 1. Similarly, by using field rheostat R2, we can adjust the field current of machine 2. Now the field excitation of machine 1 and machine 2, it is adjusted such that one will act as motor. Say for example, machine 1 acts as a motor and machine 2 will act as a generator. And here the output power of generator, that is power developed by generator, is fed back to the motor. So when machine 1 acts as motor, it will drive the generator. Generator will convert mechanical energy into electrical energy, and electrical power output of generator is fed back to the motor. And therefore the power drawn from supply, so this power drawn from supply, it is only equal to losses in machine 1 and machine 2, because here machine 1 is working as motor, it will drive the machine 2 as generator. Output of generator is fed back to motor. If there are no losses in both the machines. In that case, power drawn from supply will be equal to 0. In practice, it is not possible, and therefore whatever the losses taking place in machine 1 and machine 2, these are drawn from supply, and therefore in this case power drawn from supply is only equal to losses of two machines. So that is the main advantage of Hopkinson's test. So with very less power, we can test machine 1 as well as machine 2 at full load condition. Let us now see the procedure of test. First important step is to note down nameplate details. The safe operating limits or specifications are mentioned on nameplate of the machine. During testing, we should operate the machine within safe operating limits, and therefore before testing any machine, we should note down nameplate details. After that, connect the circuit as shown in circuit diagram. So according to this circuit diagram, we have to connect machine 1 and machine 2 back to back as per this circuit diagram. After that, we have to close the main switch, means we have to switch on the supply. Then with the help of 3-point starter, we have to start machine 1. Then we can adjust the speed of machine 1 with the help of field rheostat R1. Now field rheostat R1 must be adjusted such that machine 1 will run at its rated speed. Means we have to adjust the speed at rated value. So once the machine 1 is started, it will drive machine 2 as a generator. So here machine 1 is started as motor and machine 2 is operating as generator. Now we can adjust the voltage of generator with the help of field rheostat R2. So by changing R2, we can change the field current flowing through the field winding of generator, and we have to adjust the voltage of generator such that voltmeter V1 it shows 0 reading. So when V1 is 0 means here one end of V1 it is connected to supply voltage V. So here the voltage is supply voltage V, and other end of V1 it is connected to generated voltage. So if V1 is showing 0 means generated voltage Vg it is equal to supply voltage V, and it also indicates that main supply voltage V and generated voltage these are also same in polarity. Means here the magnitude of supply voltage and generated voltage is equal, and the polarity of V and Vg is also same. In that case only voltmeter V1 will show 0 reading. So once the voltmeter reading V1 is equal to 0, we can safely close the switch S. When the switch S is closed, now machine 1 and machine 2 will operate in parallel. Now here machine 1 is operating as motor and machine 2 is operating as generator. The output of generator, it is fed back to motor. So motor will draw power from generator as well as some small power from supply. So the power drawn from supply, it is very small. It is only equal to losses. That is losses in both machines. That is losses in machine 1 and machine 2. So the iron loss, friction and windage loss and copper loss taking place in machine 1 and machine 2 will be drawn from supply, and remaining power to motor will be supplied by generator. Now we can adjust the generating current to the desired value. So the current supplied by generator, it can be increased either by increasing the field excitation of generator, that is by increasing the field current of generator, or by reducing the field current of motor, that is by reducing the field current flowing through field winding of motor. Now after adjusting the motor current and generator current to the desired value, we have to note down the readings of different ammeters and voltmeters. So here voltmeter V, it will show supply voltage V. Ammeter A3, it shows field current drawn by motor. Then ammeter A4, it will show field current drawn by generator. Then ammeter A1, it will show the armature current of motor, and ammeter 2, it will show armature current of generator. So we have to note down all these readings, and with the help of these readings we can calculate total losses and efficiency of the machine. Let us now see what is the procedure for determination of iron and mechanical losses in machine 1 and machine 2. So here let V is equal to supply voltage in volts. Then let I is equal to current drawn by motor from supply in ampere. So current drawn by motor from supply in ampere, it is I. Then let I2 is equal to current supplied by generator in ampere. So current supplied by generator in ampere, it is I2 amperes. Then let I1 is current drawn by motor in ampere. So this current, it is I1, and I1 must be equal to I plus I2, and therefore I1, it is I plus I2. Then I3, it is exciting current of motor in ampere. So exciting current of motor in ampere, it is I3. And I4, it is exciting current of generator in ampere. So exciting current of generator in ampere, it is I4. Now let RA is armature resistance of each machine. So resistance of motor as well as resistance of generator, it is equal to RA ohm. Now the input power to the machine. So here power input, this power input, it is nothing but the product of supply voltage V and the current I. So this input power, we have seen that it supplies total iron and mechanical losses in machine 1 and machine 2, that is in motor as well as in generator, plus total armature copper loss, that is copper loss taking place in motor and in generator. So here input power to motor, it is V into I, which is equal to losses. Now here losses are armature copper loss in motor and in generator plus total iron and mechanical losses in motor and generator. Now if total armature copper loss is subtracted from input power, we will get total iron and mechanical losses. So what is the armature copper loss? So armature copper loss in motor, it is equal to square of current drawn by motor into resistance of armature, that is I1 square into Ra, and I1 is nothing but I plus I2. So it is I plus I2 bracket square into Ra, that is armature copper loss in motor. Similarly, armature copper loss in generator, it is current supplied by generator, its square into resistance of armature, that is I2 square Ra, and therefore total iron and mechanical losses, it is equal to input power, that is Vi, minus total armature copper loss. So it is Vi minus I1 square Ra, that is armature copper loss in motor, plus I2 square Ra, that is armature copper loss in generator. Now we can assume that iron loss and mechanical losses in case of both the machines are equal, because both the machines are identical. And if it is assumed that iron and mechanical losses in two machines are equal, then total iron and mechanical losses in one machine, that is iron and mechanical losses per machine W0, it is equal to Vi minus I1 square Ra plus I2 square Ra divided by 2 watts. Now using these total iron and mechanical losses in each machine, we can calculate the efficiency of motor as well as of generator. Now we have studied how to determine total iron and mechanical losses in each machine. Using these losses, we can determine efficiency of the machine when it is working as a motor and as a generator. So let us first of all see how to calculate efficiency of motor. So when the machine is working as motor, the power input to motor is power taken by armature. So this power is equal to supply voltage V into current drawn by armature of motor, that is Vi1, and power is also drawn by the field winding of motor. So this power, it is supply voltage V into current in field winding, that is I3, and therefore input power to motor P in, it is Vin, which is power supplied to armature, plus Vi3, which is power supplied to field winding. Let us now see what are the losses in motor. Now losses in motor are first of all iron and mechanical losses. then copper loss in armature and copper loss in field winding. And therefore total motor losses Wm. So this Wm, it is equal to W0. W0 is total iron and mechanical losses in motor plus I1 square Ra. So this I1 square Ra, it is armature copper loss in motor plus V into I3. So V into I3, it is filled copper loss in motor. And therefore filled copper loss plus armature copper loss plus iron and mechanical loss, it is equal to total motor losses. Now if you know the input power and losses, you can calculate output power. Now for any machine, output power P out, it is equal to input power P in minus losses, and therefore P out is equal to P in minus Wm. Wm is total motor losses. Now using output power and input power, we can calculate efficiency, and therefore motor efficiency, it is P out divided by P in into 100. So using this expression, we can calculate efficiency of motor. Similarly, we can determine efficiency of generator. Now in case of generator, output power of generator, it is generated voltage and it is equal to supply voltage V. So generated voltage multiplied by current supplied by generator, it is the power output of generator. So output power of generator, it is V into I2. I2 is current supplied by generator. So this is the output power of generator. Now what are the losses in generator? Losses in generator are iron and mechanical losses plus armature copper loss in generator plus field copper loss in generator. And therefore total generator losses, that is Wg, it is W0, that is total iron and mechanical losses plus I2 square Ra. So it is armature copper loss in generator plus V into I4. It is field copper loss in generator. Now if you know total losses and output, we can calculate input power. Now for any machine, input power P in, it is equal to output power P out plus total losses. And therefore P in, it is P out plus Wg. Now using input and output power, we can calculate efficiency of generator. So generator efficiency, it is equal to P out divided by P in into 100. So using this expression, we can determine efficiency of generator. Let us now solve one numerical problem on Hopkinson's test. Let us see first what is the data given. So here two shunt machines connected for Hopkinson's test take 20 ampere excluding field current from the main supply of 230 volt. So here supply voltage V, it is given as 230 volt and the motor input current excluding field current is 20 ampere. So this current, it is 20 ampere, and in this 20 ampere field current of motor is not included. The motor armature current is 100 ampere. So current in motor, so current drawn by motor I1, it is given as 100 ampere, and shunt field currents are 3 ampere and 2.5 ampere. So shunt field current of motor, it is 3 ampere, and shunt field current of generator, it is 2.5 ampere. If the armature resistance of each machine is 0.05 ohm, so Ra, it is equal to 0.05 ohm. Find the efficiency of each machine for this particular loading condition. So first of all, we have to calculate what is the current supplied by generator. So current supplied by generator, it is the difference of motor current I1 and input current I. And therefore generator armature current I2, it is I1 minus I. I1 is 100 and I is 20, and therefore generator armature current, it is 80 ampere. So current supplied by generator, that is I2, it is 80 ampere. So as seen earlier, most of the power comes from generator. So this current is 80 and small power is supplied from supply, which is sufficient to supply losses of two machines. So 20 ampere is supplied from main supply and 80 ampere is supplied by generator, and therefore motor current is 80 plus 20, that is 100 ampere. Now first step is to calculate mechanical and iron losses in both the machines. So for that, the input power, it is V into I. So this power input, it is supply voltage V into input current I. From this input power, if armature copper loss in motor and armature copper loss in generator, if it is subtracted, we will get iron and mechanical losses in both the machines. So first of all, we have to calculate armature copper loss in motor and armature copper loss in generator. So motor armature copper loss is I1 square Ra. So I1 is 100. So 100 square into 0.05, which is equal to 500 watt. Similarly, generator armature copper loss, it is I2 square Ra. So it is 80 square into 0.05, which is 320 watt. And therefore, total iron and mechanical losses, it is equal to Vi, that is input power, minus armature copper loss in motor and armature copper loss in generator. And therefore, it is 230 into 20 minus armature copper loss in motor, that is 500, armature copper loss in generator, that is 320. So solving this, total iron and mechanical losses in two machines, it is 3780 watt. Now these are the losses in two machines, and therefore loss in each machine W0, it is 3780 divided by 2. So total iron and mechanical losses per machine, it is 1890 watt. So using these losses, we can calculate efficiency of motor and generator. Let us first calculate the efficiency of motor. So for motor, first of all, we have to calculate what is the input power to motor. So input power to motor is supply voltage V into I1. So this is the input power to armature, V into I1, and input power to field, it is V into I3. So input power to motor, it is VI1 plus VI3, which is 230 into bracket 100 plus 3, which is 23690 watt. Now we have to calculate total loss in motor Wm. So Wm is W0. W0 is iron and mechanical loss, which is already calculated as 1890 watt. So 1890 watt plus armature copper loss in motor. So armature copper loss in motor is already calculated as 500 plus copper loss in field winding of motor. So it is V into I3. So it is equal to 230 into 3. So solving this, Wm is equal to 3080 watt. So from input power and losses, we can calculate output power. P out, it is input power minus losses. So it is equal to input power 23690 minus losses 3080, which is equal to 20610 watt. And from output and input power, we can calculate efficiency. So motor efficiency, it is P out divided by P in into 100. So solving this, we get efficiency as 86.99%. So for motor, efficiency is 86.99%. Similarly, we can calculate efficiency of generator. So output power of generator, it is voltage V into current supplied by generator. So it is 230 into 80, that is 18400 watt. Now total losses in generator Wg, it is equal to W0, that is iron and mechanical loss, which is calculated as 1890 watt plus I2 square Ra, that is armature copper loss in generator, which is already calculated as 320 watt plus V into I4. V into I4 is nothing but copper loss in field winding of generator. So substituting all the values, we get total generator losses as 2785 watt. Now from this we can calculate input power. It is output power plus losses. So it is equal to 21185 watt. Now using input and output power, we can calculate efficiency of generator. So generator efficiency is P out divided by P in into 100. Substituting P out and P in and solving, we get efficiency of generator as 86.85%. Finally, let us see what are the advantages and disadvantages of this method. Let us first see advantages. So the main advantage of this method is the method is very economical, because the power required for testing, it is very less. We have seen that power required for test, it is only equal to losses, that is losses in machine 1 and machine 2. Then the second important advantage is the machine, even if it is of large size, it can be tested at rated load condition. So we can determine actual operating conditions like temperature rise, effect of commutation, that is sparking at brushes, and these conditions can be checked at rated load. That is the main advantage of Hopkinson's test. Then results obtained from this test are fairly accurate, because we are actually loading the machine up to full load. Then there are certain disadvantages also. First limitation is we need two mechanically coupled machines, and the two machines must be identical to each other. Then only we can conduct Hopkinson's test. Then here the effect of armature reaction in case of both the machines is not same, because the two machines are not loaded equally. We have seen that load current of motor is slightly greater as compared to load current of generator, and therefore armature reaction is not same in both the cases. Then here we assume that iron losses in both the machines are equal. However, iron losses in two machines cannot be equal because field currents of two machines are not equal. So field currents of motor and generator are slightly different, and therefore flux is also different, and that's why iron losses in both machines are not equal, but we assume that the iron losses are equal. So we have studied three different methods for testing of DC machines, that is direct loading test, indirect loading test, and regenerative test. And what are the relative advantages and limitations of these tests? Thank you.